Well, I wanted to go through exam 1 with you, and what I'll do when I point this out is that there will be some problems that I consider more basic and some more advanced, and so I'll point out those as we go along. All right, well, this first page, what we're looking for here on this first problem is trying to understand what's happening and what's going on. And so obviously he's sliding down the hill. That's pretty obvious, and he has an acceleration, a tangential acceleration given by that function. And then when s is equal to 5, oops, I made a mistake here, we can see that this is actually 4.5, and we can see that that's a positive number. Acceleration is tangential and it is positive. If it's positive, then it's going in that direction. Well, if he's got a positive acceleration, that means he's speeding up, which means his tangential velocity is increasing. His normal velocity is always 0, never anything different from 0. You'll never have a 0, anything other than a 0 normal velocity. On this one, we did this demo or this simulation in class where we an object went around, and we could see that as it goes around here, there's going to be a normal component of acceleration. In this case, we see the velocity is given by that function, which means that if you take the a is equal to dv dt, you can see that a tangential is a positive number. It means it is accelerating in the tangential direction, and that acceleration is constant. What that means is that every point along the graph, there will be a tangential acceleration, tangent to the path, and it'll always be the same. So the vector, the length of the vector on those tangential acceleration pieces are all the same around the path. However, the normal acceleration will be a function of v squared over r. And so as the velocity gets bigger, the normal velocity will get bigger. And what you can see is because he's accelerating around here, velocity keeps getting bigger as you go around the path. So because the rho, or the r, and these relatively flat spots is really small, the normal acceleration is going to be small on those pieces. It's going to be 0 when he starts off here, but by the time it gets here, he's going to have a little bit of a normal acceleration. But the normal acceleration is going to be larger where you have a smaller radius, and as because over here it's the same radius as over here, but because the normal speed is, or excuse me, the speed, the tangential velocity is much larger, that will get a much greater normal component, which means that the a total will be much bigger. On this dragster thing, I was just looking for some evidence that you'd watch the video, and I was pretty generous with the points here, but basically there's around 8,000 horsepower. Dragster goes around 300 miles an hour and 1,000 feet, and it's somewhat over 3.5 seconds, 3.5 to 4 seconds, depending on which guy you're watching at what time. Now, what's going on here? When if you go around a car, or if you take your car around a corner at high speed, and the tires are squealing, and what happens when you slow down by tapping the brakes? We talked about this in class. So if you're going around a corner like this, well, actually, I can draw this, I guess. When you're going around a corner like this, and you have some speed, if you have a tangential, you'll have a force normal that's holding you in, and that force normal is going to be equal to mu mg if you're right at the very limit. If you keep that constant speed, you'll probably be able to hold on throughout the whole corner. However, if you tap your brakes and have this force tangential now, what you got here is the square root of the sum of the squares, and that total force, that force total, is now going to be greater than mu mg, which means that because of that you slide off the road. Sorry, you can't read my writing here, but I hope that you can hear what I'm saying. All right, so this is the projectile motion problem, and all these problems are pretty much the same. But if you set the x up like that, where you understand that there's a constant speed in the x direction, the x distance is how far it goes, the velocity in the x direction is cosine, and then you got a time. Up in the y direction, what you recognize is there's a constant acceleration in the negative direction, and it has some ending y, some beginning y, and then the velocity in the y direction is v sub 0 sine t, and make sure you get the right gravity in here. Some people had 9.81 instead of 32.2. But anyway, all you do is plug the numbers in, and most of the time you have a two equations, two unknowns situation. So here I solved for this for v, plugged it into here, solved for t, took that t, plugged it back into here, and solved for v. Okay. In this case, I had in this particular one, I was looking at theta is equal to 50 degrees. If you had theta equal to 55 degrees, you would have got a time of 1.5 and a speed of 33. One is the relative problem, and these again also pretty basic. They all start the same, and they all the process is all the same. And here you have to understand what is actual and what's relative. Now the actual direction and speed of the rock goes right there. He throws it here. It's actually, if it's going to hit the sign, it has to follow that line. The car, so the velocity of rock, actual, is going to have this cosine component in the I direction and sine component in the J direction. That angle alpha is, if we did that tangent there, the angle alpha is 38.7. We don't actually know the magnitude, the VR here, but we do know the direction. The A only goes in that direction, so clearly the velocity of A is going to be in the J direction. The relative term, looking at the problem, you can see that if he was standing still, he could throw at 70 feet per second. That's your clue that that's the relative term. He aims, that's another clue, at 10 degrees. So you know that this term right there is going to be the relative, and it's going to be 70 at cosine that angle, sine that angle. And so that's what we get for that. Anyway, once we get those things together, then all we do is just put them in the same equation, one equation, separate the i's and the j's on both sides of the equations, and then solve for the unknowns. In this case, the velocity of r came out of the first equation. I plug that into the second equation, and you get the velocity of A. So fairly straightforward. If in this one I did here was theta is equal to 10 degrees. If you had theta is equal to 15 degrees, you'd get a couple of different velocities here, the velocity of r of that and the velocity of A. Okay, this is another one that's fairly basic. What we're looking for here, this is a really straightforward F equals ma problem, and it was given here that the driving force is pushing the car. And then we know that wheels on the ground, they have friction, they push the car forward, they provide a tangential driving force. So that's what we're looking for. So constant force along this path, F equals ma. The distance SB here, S to 10, was just a little red herring to see if you could work through that, but the constant acceleration is given there, and that'll be the constant tangential acceleration as long as that driving force is pushing it. Doesn't matter if the path is crooked or around a corner. If it's constant driving force, then you'll have constant acceleration. So how long does it take to get to C? Well, we have to know how the distance is, and so I use the relative, constant acceleration equation of s is equal to 1/2 at squared. Knowing the s, I got 30 plus that curve there, and I get 61 meters, and find out the time is equal to 9.9 seconds. And the speed when it gets to C, again, constant acceleration. More than one way to do this. I used the v squared is equal to v sub 0 squared and 2as, and found that it was the speed was 12.39. Now, this next part, this 10-point problem, is a little more on the difficult side. This was the more advanced ones, but what is the minimum coefficient of friction for the car to stay on the road all the way to C? By the same reasoning that we did on the previous page, or one of those pages before, is that there's a pushing force, a tangential pushing force, and then there's going to be a normal force that is holding it on the track. The pushing force keeps it going straight, but the normal force makes it go around the corner. The sum of those two forces are what is the total friction when it's at the limit. When we're looking for the minimum coefficient of friction for it to stay on the road, you have to look at the sum of both of those guys. So I looked at the normal force as mv squared over rho, and I saw the mass and the velocity, which I solved for here, divided by the distance, and I got 6140. And if I look at the total force, then it's going to be the square root of the sum of the squares of that 1,000 pushing force and the 6140 normal force, and I can get the force total at 6221. Knowing that at the limit, when things are about to slip off the track, force total is equal to mu mg on a flat track, that counts, then we can solve for mu is equal to 0.79. Okay, this one is also a fairly straightforward problem. This was the roller coaster problem, and I warned you that there'd be a roller coaster or a hoop-de-doo. They both set up exactly the same way. The only difference is in the direction of the normal axis itself. So what we're looking for here is several components to this kind of a problem, but the first one is the free body diagram. You have to be able to draw the free body diagram. That's part of the solution. I'd marked you off if you didn't draw a proper free body diagram, but the free body diagram begins with the proper axes. And so the tangential axis is in the direction of motion. The normal axis point to the center of rotation. Since this is a curve this way, the normal axis points up. It's positive normal in that direction. We draw the angle theta as with the axis, the angle that the normal axis makes with the vertical, so that angle is the same as that angle. Then we draw the forces. We've got an mg and a normal force and a force of friction. Those are the three forces. We usually draw the components of the mg, where the sine going down the hill and cosine into the hill. All right, so the free body diagram is the start of that. Then you take the derivatives. The derivatives with respect to x. So we take that y equation. We take the derivative with respect to x, dy dx, and then d squared y re dx. We evaluate it at whatever x is, and we find that that is 1.25. Taking the inverse tan of that is the slope, or the 1.25 is the slope. Then we take the inverse tan to find out what that angle is. So the angle that this makes with the horizontal is the same angle that it makes with the vertical, and that's the angle that we're looking for. All right. So again, the angle that the slope makes with the horizontal is the same angle that the normal axis makes with the vertical. Anyway, find that angle. That's a very important concept. And then you find rho by plugging these numbers in there, and you find out the rho is 32. Then, so once we do the free body diagram, the derivatives, the rho, and the theta, those are all the pieces of the puzzle to feed into the sum of the forces and the normals, mass times acceleration in the normal. So all we do there is just write the equation, make sure that you write the equation properly, honor the equal sign by putting everything on the left side of the equation on the left side of the equation, and the right side of the equation on the right side of the equation, and then you start using your algebra. So in this case, we have a positive normal. Positive normal is in the positive normal axis. Mg cosine theta is in the negative, or is a negative magnitude because it's pointing away from the normal axis. Mv squared over rho, and we can solve for the normal force. If you had, okay, so that's the normal force. That was the same for both versions. The next piece was force of friction. The way we discovered the force of friction was look in the tangential axis. So let's go back to the free body diagram. Some of the forces in the tangential is mass times acceleration tangential, and I got a positive mg sine theta, a minus the force of friction, and I just plug that into the equation and solve for it, and I get force of friction is equal to 16.33, and that's all there is to it. I guess the thing to note is the acceleration tangential was given in the drawing as 12, there in the words there. If your exam had tangential acceleration of 10, then you get a force of friction of 18.81. Now the coefficient of friction, because it's a box, looking back again here, because it's a box and it's sliding, then we know that the force of friction, because it's sliding, is equal to mu normal. And so you just plug that in, and then you can solve for mu of 0.487 if you had a tangential acceleration of 12, or 0.56 if you had tangential acceleration of 10. Problem was not as straightforward. This was a fairly tough one. I know that many of you have kind of forgotten the chain rule and product rule, but we kind of spent a whole day on that on day 2, where we did a couple of class activities. We did a Socrative quiz. We did several problems in class and on the video, and you did homework. And so, I was really hoping that you'd remember this, but the way we understand this is that you did a homework problem where the airplane was taking off. And as it takes off, I ask you to calculate the airspeed. The airspeed is is the vector sum of what's going on in the x direction plus what's going on in the y direction. So in this case, the airplane's coming down, but the same thing applies. In order to find the airspeed, we have to find the vector sum of those two components. Well, one of the components is given in the picture. It says it's a constant rate descending, and I told you in the exam that descending is straight down. So that would be the y dot is coming straight down. And so our challenge is to find the x dot. We do that by taking the derivative with respect to time this time, not with respect to x. With respect to time, we have y, and then we get y dot. Using the chain rule, x goes, or 100 goes away, and you got 2x over 10,000 x dot. Now we have something to take y double dot, factor out the 2 over 10,000, and now I do the product rule of x dot. So I take x times the derivative with respect to time of x dot, which is x double dot, plus x dot times the derivative of x with respect to time, which is x dot again. So I got x double dot plus x dot squared. Evaluating those, we can see over here that y dot is a negative 25. That was given in the drawing. Solving for x dot, I can see that it is negative 625. Taking the square root of the sum of the squares of those two guys gives me the magnitude. So right here, I said x dot squared plus y dot squared square root. I get 67.5 or 67.31. That's my airspeed. The acceleration is given by looking back at the y double dot equation, and if you set y double dot is equal to 0, well, why is y double dot equal to 0? Let's look at the picture again. It says that he is descending at a constant rate of 25, which means that y dot is a constant and y double dot is equal to 0. So looking at that, we're going to say that y double dot is equal to 0, but it's also equal to that. Divide all that out, and we can set this equal to x double dot by plugging that in there. X dot was given right there, and I can see that x double dot is 1.95. Because acceleration could be, or should be, the square root of the sum of the squares of x double dot and y double dot, but since y double dot was 0, then x double dot is 1.95. Now, that's, I think, the only good way of doing this. There may be other ways that you can maybe approach this, but this is the most straightforward and the recommended way. Now, back to the airspeed, though. You can do that with the slope method, and we did this also in class, where the slope, the velocity, is the vector sum of what happens in the y direction and what happens in the x direction. You can find out what happens in the y and the x, or the relationship of that, using the slope method, knowing that dy dx is equal to 2x. Now again, this is dy dx, not dy dt, but dy dx is 2x over 10,000. Plug in the value in there, you can see the tangent theta is 0.4, and you can solve for that angle right there is 21.8. Now that you have a little vector triangle, it's pretty easy to say that v is equal to 25 over the sine of 21, and you get 67.31. Oh, gratefully, that's the same thing. And if you had the other version of the problem, there's your answers over there. The last one was also kind of a difficult one, and we did do several of these in class and on homework. So I was hoping that most people would get this, or that many people would get it. But what we've got here is this is a banked track problem, and banked track problems we solved with NTB coordinate system. And the main thing you do is draw the free body diagram. The free body diagram is over here, and you say that the n-axis points toward the middle of rotation, the b-axis points up, the t-axis actually comes in and out of the page. And so once you draw the free body diagram, recognize that there's a mass times gravity going straight down, a normal force is perpendicular to the surface, and a force of friction is tangential to the surface. The direction of the force of friction comes this way because if you went too fast, you would start sliding this way. So the force of friction is keeping you from sliding off the road going that way. All right, with all that then, we sum the forces in the B equals 0, and you can see what I've got here. I've got a mg and a cosine component of n, and then a sine component of force of friction, and it has to be equal to 0. I solved all that for normal force, and I got n is equal to that. Then I sum the forces in the tangential direction. I'm sorry, in the what did I say? I hope I said that right. The forces in the b direction. Then I sum the forces in the normal direction down here. And those have to be equal to the acceleration in the normal direction, mv squared over rho. So again, I've got a cosine component going that way of force of friction and a sine component of normal force going that way. And both of those are positive. And plug those into the equation, putting my normal force from up above right there into the equation, and I can solve for v squared, and I get that is equal to 9.1. And then if you had the other version of the problem, you got, well, I didn't put the normal force here. You'd have a little different normal force because that coefficient of friction would be a little higher. And this gets to be a little higher because of the higher coefficient of friction. And that kind of makes some sense. I think if you look at the picture, that if you had a higher coefficient of friction, you could probably drive faster without sliding off the road. And that stands to reason in the way it works. All right, I hope that this works for your explanation.